Discrete mathematics is a very important branch of mathematics. Now we start with unit number 2 of discrete mathematics, that is lattices and Boolean algebra. Now we have already defined what is the meaning of partial order relation on some set A. So partial order relation is a relation which is reflexive, antisymmetric and transitive. Now we define POSET, that is partially ordered set. A set A together with partial order relation R on it is called a partially ordered set or simply a POSET by taking P of partially, O of ordered and set. So it is a POSET. It is denoted by A comma R. So first we write set and then the partial order relation on that set. Now first example, show that the greater than or equal to relation is a partial order relation on the set of integers z. It means z together with greater than or equal to is a POSET. That is the another way of asking the question. So to show it is a partial order relation, we show it is reflexive, antisymmetric and transitive. So for reflexivity, every a in z must be related to itself. Now here for every a in z, a is greater than or equal to a. So relation is reflexive. Now for antisymmetry, we consider two elements a and b in z such that a related to b and b related to a. Means a greater than or equal to b and b greater than or equal to a. Now if both are at a time occurring, it means A equal to B. So relation is antisymmetric. Now for transitivity, we consider three elements A, B, C such that A greater than or equal to B and B greater than or equal to C. Then A greater than or equal to C. That means A related to C. So relation is transitive. Now as relation is reflexive, antisymmetric and transitive, it is a partial order relation on the set of integers z, and hence z together with greater than or equal to relation is a POSET. Now similar to that here, less than or equal to relation is a partial order relation on the set of real numbers R. Again in the same way we can show that it is a partial order relation. Similarly, n with less than or equal to z with less than or equal to are also posets. Generally, the partial order relation is denoted by this symbol, which is less than or equal to symbol. But we are not writing and reading like less than or equal to right now. Hereafter, we will denote a partial order relation by that symbol. But instead of reading it as a less than or equal to b, we read this as a precedes b. Now next example, define a divisibility relation on n. That is a precedes b. This is not less than or equal to now. This is just the notation. So a precedes b if and only if a divides b. So that this relation is a partial order relation on n. So again we check the three properties. First is reflexive. So for reflexivity we have to show a precedes a, means a related to a. Now check the condition. Now every natural number a divides itself, and so a precedes a means the relation is reflexive. Now for antisymmetry we take two natural numbers a and b such that a related to b and b related to a. That is a precedes b and b precedes a. So by definition of relation we get a divides b and b divides a. So a and b are equal. Now here a and b are natural numbers. So we can write if a divides b, b divides a, then they are equal. If it is a set of integers, then we can't write this. For example, if a is 2 and b is minus 2, then 2 divides minus 2 and minus 2 divides 2. So both happens, but 2 and minus 2 are not equal. But in this case, it is a set of natural numbers, so there are no negative numbers. So if a divides b and b divides a, it means a and b are equal, and hence the relation is antisymmetric. Now for transitivity, we take three numbers a, b, c in n such that a is related to b and b is related to c. Means a precedes b and b precedes c. So by definition, a divides b and b divides c implies a divides c. Means a precedes c. So the relation is transitive. Now as the relation is reflexive, antisymmetric and transitive, it is a partial order relation on set of natural numbers n. So n together with this relation means together with divisibility relation is a POSET. Now this is very important relation which we are using in further examples. Now one more example. Let S be any set and PS denote the power set of S, that is set of all subsets of S. Define set inclusion relation on PS, that is for xy in P of S, x is related to y if and only if x is subset of y. Show that PS with R is a POSET. So again we check for reflexivity, antisymmetry and transitivity. Now P of S is the set of all subsets of S. So we are denoting members of PS by capital letters. Now the first part reflexivity means X is related to X. Now as every set is subset of itself, we can write X subset of X for every X in PX. Means X is related to X for every X in PS and hence the relation is reflexive. Now for antisymmetry, we consider xy in PS such that x related to y and y related to x. So by definition of relation, x is subset of y and y is subset of x. This implies x equal to y and hence R is antisymmetry. Now for transitivity, we consider three members of PS, say x, y, z, such that x is related to y and y is related to z. Then by definition of relation, x is subset of y and y is subset of z implies x subset of z. Hence, x is related to z. That means the relation is transitive. It means R is reflexive, antisymmetric and transitive. So R is a partial order relation on PS. Hence PSR is a POSET. Now hash diagram. Now it is a special type of directed graph which is drawn for a finite POSET with following conventions. So hash diagram is drawn only for finite POSET means partially ordered set. Now what are the conventions while drawing the hash diagram? Denote the elements by vertices. Since the partial order relation is reflexive, there is a self loop at each vertex. We don't show these loops. Then remove all edges that must be present due to transitivity. For example, if A is related to B and B related to C, then this implies that A related to C. So we remove A, R, C. That means by joining AB and BC, it follows that A is related to C. So it is not necessary to draw a line segment from A to C separately. If A is related to B, then we put A at a lower level and B at upper level. So A must be at a lower level than B. Now we assume that all arrows point upward. So we remove the directions of the arrows. Now, using the conventions for drawing hash diagram, now we draw the hash diagram representing the partial order relation divisibility on the set A is equal to 1, 2, 3, 4, 6, 12. That is here A precedes B if and only if A divides B. Now similar to divisibility relation on A, this relation of divisibility is a partial order relation on A which is subset of N. Now we write that relation in terms of ordered pairs. Now the relation is equal to ordered pair AB in across A such that A divides B. Now as 1 divides every element of A, 1 is related to each element of A. So we write all the pairs 1, 1, 1, 2, 1, 3, 1, 4, 1, 6, 1, 12. Now 2 divides 2, 4, 6, 12. So we write 2, 2, 2, 4, 2, 6, 2, 12. 3 divides 3, 6 and 12. So 3, 3, 3, 6, 3, 12. As 4 divides 4 and 12, we get 4, 4 and 4, 12. 6 divides 6 and 12, so 6, 6 and 6, 12. And 12 divides 12, so we write 12, comma 12. So this is the relation defined on that set A. Now to draw the hash diagram, we represent 1, 2, 3, 4, 6, 12 each element by some small circle. Now as 1 divides every element but there is no element which divides 1 in this case, 1 is at lowest level. So we start with 1. So we represent 1 by small circle, and there is no element below that 1 because no element divides 1 from that set. Now 1 divides 2 and 1 divides 3, and this relationship is directly, it means there is no element in between such that 1 divides a and a divides 2, or 1 divides a and a divides 3. So above 1 we take 2 and 3 and we join them by line segment. We are not showing directions because all the directions are in upward direction only, that is the convention. So one related to 2, one related to 3, that part we have shown. Now 2 actually related to 2, but we are not showing any self loop. Then 2 is related to 4. It means 2 divides 4. Again, this relationship is direct. That means there is no element a such that 2 divides a and a divides 4. So for 2 divides 4, we take 4 above 2 and we join them by line segment. Then 2 divides 6. Again, there is no element a such that 2 divides a and a divides 6. So directly we have to show that 2 is related to 6. So above 2 we have to take 6 somewhere and then we join them by line segment. But I have not taken here above 4 because actually 4 is not related to 6. So it is above 2 to the right side. Then 2 12. If you consider, actually 2 divides 12, that is true, but 2 divides 4 and 4 divides 12. That means there exists 4 in a such that 2 divides 4, 4 divides 12. So this relation we can show via 4. So as 2 is related to 4 and 4 related to 12, directly we can draw line segment for 4 to 12, and not necessary to draw the line segment from 2 to 12 separately. Then 3 3, that is self loop, which we are not showing. Then 3 divides 6 directly. So 3 6 we have to draw the line segment. Then 3 12. Again 3 divides 12, but there is 6 such that 3 divides 6 and 6 divides 12. So for 3 6 we have shown by line segment. Same way, draw the line segment from 6 to 12. So by transitivity we get 3 divides 12, that part. Now 4 4 loop, again which we are not showing. 4 12. So 4 is directly related to 12. So we have drawn the line segment. 6 12 already we have done, and 12 12 we are not showing as it is a loop. So in this way we can draw the hash diagram. Now the set A in above example consists of all divisors of 12. In general, for any positive integer n, the set of positive divisors of n is denoted by dn. So actually this set is set of all positive divisors of 12, means we can denote it by d12 also. Note that dn with the divides relation forms a POSET. Now, similar to previous question, this is one more example. Draw the hash diagram of the POSET D42, the set of all divisors of 42 with respect to partial order relation divides. Now, D42 is nothing but set of all positive divisors of 42. So, it contains 1, 2, 3, 6, 7, 14, 21 and 42. Now, consider the relation of divisibility. We can write the relation in terms of ordered pairs, and similar to previous question we can draw the hash diagram. Now A is equal to ABC. Consider the partial ordering relation on set A, which is set inclusion relation. Now draw the hash diagram for P of A with set inclusion relation. Now A is ABC. Now what is P of A? Set of all subsets of A which contains phi, singleton A, singleton B, singleton C, then AB, BC, AC and ABC. Now here the relation is like for xy in A, P of A, x is related to y if and only if x is subset of y. Now there is no element in P of A which is subset of phi, means no element is related to phi. So phi is at lowest level. Now phi is subset of every set actually. So phi is related to each element. But if you observe here, phi is subset of singleton A, singleton B, singleton C directly. Means there is no set X such that phi subset of X and subset of singleton A. So above phi At upper level, we have to take three elements singleton A, singleton B, singleton C, and we join phi to singleton A, phi to singleton B, and phi to singleton C as they are related. Now see singleton A. Now singleton A is subset of AB and ABC, but singleton A, there exists AB such that singleton A is subset of AB, subset of ABC. So singleton A is related to ABC, that is related elements by transitivity. So we can show them through AB. But A is related to AB directly. So above A we show AB and draw the line segment. Similarly, singleton B is subset of AB which we show directly. Same way, singleton B is subset of BC which we show directly, and same way for C. Now AB is subset of ABC and there is no set X such that AB subset of X subset of ABC. So this relationship is directly. But now as A is subset of AB and AB is subset of ABC, by transitivity A is subset of ABC. Means A related to ABC that we got. So in this way you can complete the diagram. Now, from the hash diagram given below, find the relation and the corresponding set. Now, in previous examples, we have given the relation and we have drawn the hash diagram. Now, for the hash diagram, we have to write the corresponding relation. Now, first see which elements are present in that diagram. A, B, C, D. It means that relation is defined on set containing A, B, C, D. Now, first, as every element is related to itself as it is a reflexive relation, we write all the pairs AA, BB, CC and BD. Now see here above A, C is there and A to C directed line segment is there. So A related to C. Similarly, above CD is there and C to D there is a line segment. It means C is related to D. Now AC is there, CD is there. So by transitivity, A is related to D. So we get AD also. Now above B, C is there and B to C there is line segment. So it is B comma C pair. Now C comma D already we have written. Now by transitivity B related to C, C related to D means B related to D. So these are the pairs present in that relation. So from the hash diagram also we can interpret the relation.